All right, hello everyone. I hope all of you are doing great. So today I'm going to be attempting Codeforces round 849. Now this is going to be a Division 4 round. It's not going to be rated for me. And so the main agenda for today is that I won't be caring much about what rank I'll get. Instead, I'll try to be as clear as possible in stating what I'm thinking so that you guys get to know how I think during contests and you can get to know a clear idea of the solutions, right? Also, this is probably going to be my last contest before I go on a short 1 week break from CP since I have my mid-semester exams next week, right? So yeah, let's get right onto it. Hmm. As always, it's taking a lot of time to load the first problem. All right, so we have our first problem. Given a lowercase Latin character, check if it appears in the string Codeforces. Okay, so this is pretty easy. All you need to do to solve it in a good way is like there is a bad solution. The bad solution is that you can check the character being equal to Codeforces. But like a good way to solve this during contest and a clean way to do it would be to know have a string called code forces in your code and then just iterate on that string and check whether any character of that string is equal to the character that you have in the input. And if that's the case, then you should output yes, right? So let's just quickly do that. What I'm trying to say is let's have a string s is equal to code forces. And then what you'll do is you have a character in the input, you'll read it, and then just go over all the characters in the string s. And if x is equal to the character that you have in the input, then the answer is going to be yes. Right. So we just do that. So this is a much cleaner way to write it out. Hopefully this is going to work. All right, let's submit this and move on. There are 8 problems. That's nice. For some reason, Codeforces is really slow today. Okay, so we have the second problem. Some guy is standing at the point 0, 0, and he's given a string s of length n and he performs n moves. So the ith moves is as follows. So depending on what character the ith character of the string is, the person moves either left, right, up and down. Pretty cool. So now there is a candy at 1, 1, and you need to determine if I ever pass that candy. All right. So this is again a pretty simple problem. So what you can do is you can just maintain your current position every time and just check whether your position currently is 1, 1 or not. If your position is 1, 1 at any point of time, then you can safely output yes, right? Again, I don't think much explanation is needed to solve this problem. So let's just quickly code it up. So in the input, we have n and then we have a string s, right? Cool. So let's have the string s, read into it, and let's maintain two variables. Initially, both of them are 0 since I am at the point 0, 0, which is the origin, right? And then what I'll do is I'll iterate over all the characters. And again, if the current character is L, okay, so let's say this is C. So if the current character is L, then I'll go left. Going left means decreasing my x coordinate. So I'll say x minus minus. Else, if the current character is right, then I will increment my x coordinate. Otherwise, if the current character is D, that means I'm going down, so I'm going to decrement my y coordinate. Otherwise, we know that it is U, so I'll be going up, so I'll be incrementing my y coordinate. And if at any point of my journey, if I ever get that x is equal to 1 and y is equal to 1, then I have reached the final destination. So I will simply say that the answer now is going to be yes. So yeah, hopefully this is going to work. Cool. Let's submit this, move on to problem C. All right, so initially we have a binary string S, possibly of length 0. That's weird. And what we're going to do is we perform the following operation several times. Add 0 to one end of the string and 1 to the other end of the string. Okay. All right. You are given the final string. What is the length of the shortest possible string he could have started with? Okay. All right. So we look at that just before getting the confirmation that we got B, but we're not getting that. So let's see how we can solve this problem. So initially we have certain string to begin with, right? So this is the string that we had. Let's say it is something, we don't care what it is right now. Now, in one operation, what we are doing according to the problem is that we are adding a 1 to one end and a 0 to the other end, right? So let's say that we add a 0 here, then we have to add a 1 here, right? Similarly, in the next operation, let's say we add a 1 here, so we'll have to add a 0 here in the suffix. And this goes on forever, right? So if you want to find the minimal length of the string that we started with, then it's just to say that we need to find the maximal length of this prefix and suffix combination such that the value at prefix is not equal to the value at suffix. So if s of 0 is not equal to s of n minus 1, then that means that these two numbers, s of 0 and s of n minus 1, they could have been a part of an operation. So then if this is the case, let's say we maintain two variables, initially I is equal to 0 and j is equal to n minus 1. So if this is the case, then I can safely increment my answer and I can say that I is increasing and j is decreasing. So then I will now look at s of 1 and s of n minus 2. And this is something which keeps on happening, right? So I can just check for how many elements in the prefix and suffix uh, this happens, and that is going to be my answer, right? Cool. So I hope the solution is clear enough. Let's now code it up. All right. So we have n in a string of length n. Now, obviously, if we have a prefix of length x which satisfies this condition, then the first x character and the last x characters were uh, due to the operation that we did. So the final length of the initial string would become n minus 2x. So we need to maximize x in order to minimize n minus 2x. And the answer is going to be n minus 2x. All right, so let's say we have a string s. See, in s, initially our answer is going to be 0, right? Now what we'll do is we'll say I is equal to 0 and j is equals to n minus 1. Now, while I is strictly smaller than j, we'll perform something. Obviously, if I is equal to j, then we can't say that both I and j, si and sj came from an operation, right? Because they are the same character. So all we need to check is if s of I is not equal to s of j, we'll say increment your answer, increment I, decrement j. Else, we know that we have broken the chain, so we can simply break out of the loop. And finally, we can say answer is equal to n minus 2 into answer. So yeah, hopefully this is going to work. Cool. Let's submit this and move on to the next problem. There is quite a big queue today. I mean, there has been there have been quite some things which are happening with Codeforces, which I don't think are right, since the ratings haven't been updated. Like they just got updated a few minutes before the start of this round. So that's something which is a bit shady. So I don't know what's going on with that, but it's somehow connected to why it's so slow today. Anyways, let's focus on problem D. We are done with three problems. We have five more to go. All right. So let's denote fx function for a string s as the number of distinct characters in the string. All right. So we are given a string s. We have to split it into two non-empty strings a and b such that f of a plus f of b is the maximum possible. In other words, we need to find the maximum possible value of f of a plus f of b such that a plus b is equal to s. All right. This seems like a pretty nice problem. So again, there might be a better way to do this, but what's coming to my mind is that we have a string s, right? So we have a string s, and what we can do is we can calculate for each prefix and for each suffix how many distinct characters are present, and then we can just iterate on, oh, maybe wait a second. What do we have to do? Fa plus fb is maximum possible, and a plus b is equal to s, right? Yeah. So we need to break it at some point. So let's say we break it at this particular point. So all we need to do is we need to check how many distinct characters are present here and how many distinct characters are present here. And we can pretty much use any data structure that we want to pre-compute these values for each prefix and for each suffix. So if we have a value pre of I, which denotes the number of distinct characters in the first I positions, or not in the first I positions, up till index I. And similarly, we have suf of I, which denotes number of distinct characters from I to n minus 1. So let's say we break this string at point I, then f of A is going to be pre of I, and f of B is going to be suf of I plus 1. And hopefully both these strings have to be non-empty. Yeah. All right. So yeah, that's exactly what we need to do. So we can just iterate for I and then maximize this value pre of I plus suf of I plus 1. And that's going to be our answer. All right, let's code it up. So we have a string s. So we have a vector pre, and similarly we have a vector suf. Now let's compute pre. So for that we have a set of characters, let's say, and we iterate over all the positions from 0 to n minus 1. And we'll say insert the particular character at the ith position into the set. And pre of I is going to be nothing but the size of the set that we have. Okay, now I'll use the same set, I'll clear it up, and then I'll iterate in reverse direction to calculate suf of I for all I. And I'll say st.insert s of I, and suf of I is going to be the size of the set. And then I will iterate on where I'm breaking the string. So I can break the string from anywhere from 0 to n minus 2. What happens if n is equal to 1? So n is never 1. So if I break it at point I, all I need to do is I need to maximize my answer with pre of I plus suf of I plus 1. And yeah, that should work. Apparently that does not work. Now, why is that? Number of distinct characters the string contains. That's because we are not reading the string. And now it works. Cool. So let's submit this thing. All right, let's move on to problem E since the queue is like really heavy today. There's no point in waiting to check. It's going to take quite a lot of time. All right, so given an array A consisting of n elements, we need to find the maximum possible sum the array can have after performing the following operation any number of times. So we can choose two adjacent elements and flip both of their signs. In other words, choose an index I such that I is from 1 to n minus 1 and design and assign AI equal to minus AI and AI plus 1 equal to minus AI plus 1. Yeah, that certainly makes sense. The elements can be negative as well. Cool. So let's think about this problem for a while and see, like design various cases and let's just see what happens in several cases. Okay. So let's say we have an index I and we have I plus 1. And there are a few cases. First of all, let's say at I we have an element which is less than 0. At j we have an element which is less than 0. And let's say that the absolute value of the element at I, so the absolute value is equal to x, and the absolute value at I plus 1, this is equal to y. Okay. So here what happens is, in this case, we get a gain of x plus y. So it is always optimal to do the operation when both I and I plus 1 are negative. Similarly, let's say that I is negative, or let's say that both are positive. So now we are saying that, so this is AI, this is AI plus 1. So now we say that AI is positive, AI plus 1 is positive. This should be 2x plus 2y because initially we had a minus x and now we have a plus x. Similarly, we had a minus y, now we had a plus y. Now let's see here what's happening. Here the exact reverse of this will happen. And instead of getting a benefit of 2x plus 2y, we'll get a loss of minus 2x minus 2y. So in a sense, we can say that it is never optimal to change when both of them are positive. All right, makes sense. Or maybe somehow it would be possible. I don't think, I highly doubt that would be the case. Yeah, that shouldn't happen. Anyways, let's just analyze all the cases. So let's say AI is less than 0 and AI plus 1 is greater than 0. Now what happens here is that since AI is less than 0, AI is minus x and it becomes plus x, so we get a gain of 2x. And similarly, we get a loss of 2y. And in the other case, what we'll get is we'll get a gain of 2y and we'll get a loss of 2x. So this is all that we have. Cool. Makes total sense. Hmm. Now let's see in if there is any case such that we are in case 1, both of them are, sorry, we are in case 2, and we still do that operation somehow. Our final goal is to have as many positive elements as possible, right? So let's say we have a chain of negative elements. All of these elements are negative, right? And let's say that the length of this chain is even. So if the length of this chain is even, then we can just pair up all these elements and we can say that we can convert all of them to positives. But what happens if the length of this chain is odd? So do both these elements have to be adjacent? Yeah, they do. So let's say now that this chain is odd. Now what can we say about the elements? Here there might be some positive element or not. And again, here there might be some positive element, or there may or may not be some positive elements here. Now, what can we say about this? Hmm. So we have some negatives, then we have some positives, then we have again some negatives, then some positives, some negatives. And let's say this is how the array looks like. All right, so let's think about it like this. So let's look at the first two characters. If both of them are positive, then we just go to the third character. If the first is positive, then second is negative, we just go to the second character. And similarly, if both of them are negative, we perform this operation, convert both of them to positive, and then we go to the next character. And similarly, let's say the first one is negative and the other one is positive. We will perform this operation. So we simply perform this operation, convert it to plus minus, and then we go to the second operation, to the second index, right? So all that is telling me is that towards the end, towards the end, what will happen is that I will end up with everything positive, and the last element may or may not be negative. But in which case will the last element be negative? Well, we can note one thing that we never really change the parity of the number of negative elements, right? So here we are adding, if we do an operation here, we get minus minus. So we are just adding two negative elements. Here nothing happens. Here again, we are removing two negative elements. So yeah, we never change the parity of negative elements. So if the negative elements initially were odd, then we can say that this last element is going to be negative. Initially, if they were even, then we can say that we can convert all the elements positive at the end of the day, right? That makes sense. But another good thing here is that now once we have this negative element, we can do operations in such a way that we can shift this negative element to any index that we want, right? So the answer is going to look like that. We'll sort the array. We'll find out the parity of the number of negative elements. Or maybe we don't even sort the array. We just find out the parity of the number of negative elements. If the parity is even, then we can say that we can always convert all the negative elements to positive elements. So we can just take the sum of absolute values. But if that's not the case, what we'll do is it is totally our choice to make an element negative, and we'll make the smallest possible element as the negative element, the element which has the smallest possible absolute value. And we'll take the total sum of absolute values and we'll just subtract 2 into this 2 into the sum of the element which has the smallest absolute value. Because in the case where the number of negative elements is odd, we'll always end up with at least one negative element. So yeah, hopefully this is going to work. Yeah. Let's read into the array. And first of all, we'll say that our answer is equal to absolute value of AI, the summation of all of them. Another thing we need is we need the count of the number of negative elements. So if AI is less than 0, then we say increment the count. Another thing that we need is we need the element with the minimum absolute value. So let's initialize it with infinity, and we'll say mn is equal to min mn and absolute value of AI. Finally, if count is even, then we'll do nothing. But okay, so let's just not make this case. So if count is odd, then we know that at least one element has to be negative, so it might as well be the smallest element. So we'll say answer minus equal to 2 into mn. Hopefully this is going to be correct. Yep, works. So yeah, let's submit this. We got the first 4 problems right. That's good. So the name of problem F sounds interesting. Range update point query. Awesome. All right, let's go to problem F now. So given an array, you need to handle a total of q updates and queries of 2 types. One LR for each index I in L to R, update the value of AI to the sum of digits of AI. All right, that's quite interesting. And the second type of query is to output AX. All right, looks interesting. So we need to update AI to the sum of digits of AI. An interesting observation to make is that since AI is less than 10 raised to the power 9, if we do an operation once on an I, then it will automatically be smaller than some number, which is the maximum possible sum of digits of a number which is smaller than 10 raised to the power 9. Smaller than or equal to. Let's say smaller than, because if it is equal to 10 raised to the power 9, then the sum of digits is obviously going to be just 1, right? So if it is smaller than 10 raised to the power 9, then it has 9 digits and all 9 of them can be 9. So the maximum sum of digits is going to be 81. So as soon as we perform one operation on any index, it becomes less than or equal to 81 for sure. That's a nice observation to have. And the reason for that is that if we know that all the numbers are from 1 to 81, then it becomes quite easy to handle stuff, right? Hmm. Okay, so I have a solution in mind and let's discuss that solution. Okay, so we know that after one operation, the maximum sum of digits of any number can be what? Now, just forget about doing an operation. Let's say that we have a number less than 10 raised to the power 9. So it will have at max 9 digits, right? If it is equal to 10 raised to the power 9, then the sum of digits obviously becomes 1. So now it has 9 digits and all 9 of them can be equal to 9. So the sum of digits becomes 81, and this is the maximum possible sum of digits, right? So now let's say we have this number 81. The sum of digits of this becomes 9. And let's say we have again a number. So now, once we have this number 9, what we can say is that the sum of digits remains 9, right? It always stays 9. And the same is true for, let's say, any number. So the first time that the sum of digits becomes single digit, it then remains constant. It will never change. And that is something that we can use in our solution. So a way to do this would be to have a lazy segment tree, and let's just count the number of times we include an element. And if we say that, let's say we have included an element 5 times, so we can handle those we can handle those increment updates using a lazy segment tree. And then what we can do is we can simply say that, okay, we have done it 5 times. So let's just say that the initial number was x and just apply this operation on x 5 times. But what we notice is that, let's say x was this number only. What we notice is that as soon as we apply it for the second time, the sum of digits becomes equal to 2. The sum of digits becomes equal to 9, right? And that's bad because the sum of digits is equal to 9, and uh, after two operations, it's not going to change at all, right? So that's helpful for us because we can stop after only two operations. We don't need to apply all the 5 operations. Right. So this is actually not the worst case. The number of operations that it takes to become two digit can be larger than this, probably, because let's say instead of 81, we had 56 as the sum of digits. So if that is the case, we'll have 11 and then we'll have 2. And initially we started with the number x. So it's taking 3 operations for us to get there. But what I'm interested in is to have a solution which does not use any kind of lazy segment trees, right? Hmm. So let's think about it for 5 minutes. And if I cannot come up with anything else, then I'll simply code it up. I mean, a lazy segment tree is not needed here since we have only point queries. But if we had range queries, then we would have needed it. That's a different thing. Although it will suffice. But since this is a div 4 round, I don't think that's actually an intended solution to this problem. All right, let's think about it. I think there is a solution in my mind. Okay, so let's see what we can do. So what we can do here is that we can maintain a set of elements, right? So we can maintain a set of indices. And in my set, what I'm going to do is, in my set, I'm going to store all the indices which have not yet become single digit. Okay, cool. So this is something that I can do. And let's say I have this set with me. So what I can do to handle a range update query is that I can just keep taking the lower bound of L in my set. And once I take a lower bound of L, I will get a number, right? And if that number is less than or equal to R, then that means I have an index I, which still needs to get changed, and it is in the range from L to R. So I will look at the value of AI and then I will just convert it to the sum of its digits. And then I'll check whether the sum of digits has become single digit or not. If that's the case, then I will remove it from my set. Okay. And yeah, that's going to work. In this way, I can keep all the values updated. The catch here is that in at most 4 or 5 operations, every element will be removed from the set. So the time complexity still remains n log n. Cool. So I think that's the solution we are interested in. All right. I hope it's clear enough. If it's not, then it'll definitely get clear when I code it up. Okay. So what I'm going to do here is that I'll have a set. So this will store all the indices which are currently greater than 9. So if AI is greater than 9, you can say st.insert I. Cool. So now we iterate on all the queries. We'll read into the type of the query. So if type is equal to 1, it's an update query. Else we have an index, right? Here we have LR and here we have index. Cool. So we'll read into X and we'll simply output A of X. And now what we are going to do is we are going to read in L and R and we are going to iterate in our set. So what we'll do is we'll take the lower bound of this number L and we'll check if the index present at this point is less than or equal to R or not. Now, if that is the case, what we'll do is, so let's say we have a function which converts a number to its sum of digits, right? So convert to sum of digits. So it will take a number n. So I'll just convert this number n to a string. So string s would be toString of n. I'll have an element answer is equal to 0. And then I'll just iterate on this string. And I'll say answer plus is equal to s minus 0. This is the digit at that position. And then I'll return answer. X minus 0. Yeah. Okay, so if that is the case, then what I'll do is I'll do a of star it is equal to convert to SOT of a of star it. And now I'll check if a of star it, if this becomes less than 10, then I will remove it from my set. And also I don't need to take the lower bound of L, I need to take the lower bound of the previous element that I was having, because it's possible that I don't remove it. So let's say we take the lower bound of the previous element, then we'll erase it from the set. And in any case, I will say prev is equal to star it. Let's do it here. Cool. But if star it is greater than R, then I have exhausted the range. So in that case, I'm going to break. Yeah. So this looks like it's going to work. It's not working somehow. Oh, I was logged out. That's not what I wanted. So we got accepted on E. It's not a problem. So yeah, apparently this is going on an infinite loop. So let's see what the problem is here. Works now. So there is some problem in the while loop for sure. Let's see what it is. Let's try to output the sum of digits. If that function works good. So 1, 2, something like this. 13, is that correct? Yeah, so there's no problem with the function. Let's see. So we are, oh, this should be upper bound. Yeah. And this should be L minus 1. Also, if it is equal to st dot end, then we need to break. Now this should work. I'm not verifying whether it's correct or not. Okay, some problems. That's because I copied the wrong test case. Cool, this works. So let's submit it. I hope the solution is clear. Just give me a moment. Yeah, all right. So did we get it? So they logged me out again. That's not done at all. That's just not done. Something is seriously wrong with Codeforces today. Anyways, let's focus on G1 and G2. We are down to the last two problems. So the only difference between the easy and hard versions are the locations you can teleport to. Consider so these are not different by constraints, so there is some logical difference between the problems. So I think I'll have to, I mean, G1 is probably not a subpart of G2, so I'll have to solve both of them separately. So we need to consider the points from 0 to n on a number line, and there is a teleporter which is located on each of the points from 1 to n. At point I, you can do the following. We can move left 1 unit, it costs 1 coin. We can move right 1 unit, again costs 1 coin. Or we can use a teleporter at point I if it exists. So it costs AI coins, and as a result, we teleport to point 0. Once you use a teleporter, you cannot use it again. Okay. You have C coins and you start at point 0. What's the most number of teleporters you can use? Oh, that's interesting. That's really interesting. So if this is G1, what's G2? As a result, you choose whether to go to point 0 or n plus 1. So that's quite different. Let's focus on G1 for now. Looks like some kind of an ad hoc problem. All right, let's write it down, see what we can get. We need to use the most number of teleporters. Okay, so the situation looks something like this. We are currently at point 0. We have all these points from 1 to n, and right, we have points from 1 to n. Number of coins you have, the following. What's the most? So our only goal is to use the teleporters. We don't need to end up at any point. That's also good. That's a good thing. So are there teleporters at every point from 1 to n? Two integers, then n space the cost to use the teleporters. Use a teleporter at point I if it exists. Oh yeah, so there is a teleporter at each point from 1 to n, but the costs are different. That makes sense. So there is a teleporter at each of these points. Okay. And our final goal is to go from the point, uh, no, our final goal is to just use as many teleporters as we want to use. Okay. The value of C is quite large, so it makes sense that we don't use dynamic programming, or maybe in some way we can, but let's not think about that for now. So when we use a teleporter, let's say we use this teleporter, we go here to point number 3, spending 3 coins. Okay. And then we use a teleporter. So the teleporter teleports us back here. And now let's say we decide to use the teleporter at point 2. So now we again go here, spending 2 coins, and then we get back here. Obviously, we use A2 plus A3 plus 3 plus 2 coins, right? But instead, if we go to A2 first and use the teleporter and then go to A3, that's allowed, right? Then what happens? So then we'll spend 2 coins, then we'll spend A2 coins, then we'll spend 3 coins, and then we'll spend A3 coins. So it doesn't really matter how we go. Is it ever optimal for us to spend a coin to go left? I don't think so. So the point that I'm trying to make is let's say that we have a set of all the elevators that all the, what do we call it? Teleports. So let's say we have a set of all the teleporters that we have, x1, x2, up till xk. Let's say we use k of these teleporters. So what I'm claiming is that it doesn't matter in which order I use these teleporters, because I will literally never be going left. Going left is like just wasting time for me, because as soon as I use an elevator, I will always end up at position 0. So let's say I use the teleporter at position x1. So it will definitely cost me x1 plus a of x1 coins. Similarly, for x2, it will always cost me x2 plus a of x2 coins. Similarly, for xk, it will always cost me xk plus a of xk coins. So all that means is that I can do some greedy thing. What I'll do is, for all I will say that ai is equal to ai plus I, and then I'll just greedily pick the smallest value of ai, and I'll keep picking it until and unless I run out of coins. So I hope this is correct and clear enough, because I don't think going left ever makes any sense. Yeah. All right. So this is good enough. I hope it's clear as well. So we have NC and then we have the elements. Cool. So we have a vector. Let's read it. So what we'll do is we'll say AI plus equal to I, and then we'll sort the vector. And now we simply iterate it from 1 to n. So if C is greater than or equal to A of I, then we'll say answer plus plus and C minus equal to A of I. And finally, I will just output my answer. So hopefully this is going to work. Yes, it does. Let's submit this and move on to the last task. So we got F as well. That's nice. So I think G2 is quite hard since only 62 people have got it till now. Cool. Let's see. So now the points are from 0 to n plus 1, and there is again a teleporter at all points from 1 to n. And at point I, you can do the following. You can move left 1 unit. Damn it, I've again been logged out. This is like really frustrating. Cool. So again, we can move left, we can move right. So you can use a teleporter at point I if it exists. It costs AI coins. As a result, now we decide whether we go to point 0 or point n plus 1. So once you use a teleporter, you can't use it again. Cool. So again, let's analyze how things change here. So this is our point 0. Then we have all these teleporters. And this is our point n plus 1. Let's say we first, so initially, where are we? So we start at point 0. Okay. So let's say first we decide to choose the fifth teleporter. So we decide to choose the fifth teleporter and we go to point n plus 1. That's the choice that we made. And then let's say we came left and we used this elevator. Let's say the ninth teleporter. So this is the ninth teleporter. So we come here and we again decide to go to the point n plus 1. So what happens now? Let's see how many coins did we put in. So first we spent 5 coins, then we spent A5 coins. Okay. Then how many coins did we spend? What is n? 12. So n is 12, right? So what we did is we were at 13 and we went to 9. So that gives us 4 coins. And then we spent A of 9 coins, right? Instead, if we had decided to go to the point 0 instead of n plus 1, then what would have happened? First, again, we would have spent 5 coins, then we'll spend A5 coins. But now we are at point 0, so instead of 13 minus 9, we'll give it a straight 9 plus A of 9. Okay. Another thing we can notice here is that it's completely our choice to make it 13 minus 9 or 9. And it depends on where we go when we use this teleporter. Yeah, cool. So let's say we have a set of elevators again that we will be using. Let's say this is the optimal set x1, x2, x3 up till xk. Now, for the first teleporter x1, we don't really have a choice. The cost will have to be x1 plus a of x1. But for all these remaining elevators, I have a choice for the cost to be xi plus a of xi or n plus 1 minus xi plus a of xi, right? That makes perfect sense. Yeah. Cool. So what can we do now? So what we can do is, again, instead of just having xi plus a of xi, we can take the minimum of these two values. Okay, and we can again sort the vector that we had. But now the thing is that when we iterate on the prefix and we find out the optimal prefix, there are two cases. One case is that there is at least one element for which this is the minimum, for which this is the minimum. So if there is at least one element for which this is the minimum, we can just have that element as our first element, and the others can be anything we want. But the bad case is that for all elements, this is the minimum, right? So let's say these are for the elements for which this is the minimum are type 1 elements, and these elements are type 2 elements for which this is the minimum. So if in the optimal prefix, all the elements, at least one element is a type 1 element, then our prefix is good enough. We have the answer. But if there is at least one type, if all the elements in the prefix are type 2, then that's going to be bad. Okay. So then what we'll do is that we have our array sorted. Okay. So let's say this is the prefix that we are taking of the first five elements, and all of them are type 2 elements. So that's definitely bad. So one case is that we arbitrarily convert one element from these five elements to a type 1 element, and we take that. That's something that we can do. But the other case is that the type 1 element is coming from here. So that's again going to be convenient, because since the type 1 element is coming from here, we can just skip out this last element and we can take only these elements, right? So I think that's all that we need to do. Just form two cases. And in the second case, there are again two cases that the type 1 element comes from here or it comes from here. All right, I think it's clear enough. Let's now code it up. So let's create a new file and let's save it as g2.cpp. Hmm. So we'll have a vector of pairs, we'll sort it, and we can also have the type. Yeah, makes sense. Cool. So the input format still says the same. Just a moment. So we need to make sure that the sum is less than equal to C, right? Again, another thing that we can do here is that, let's say we have this sorted vector. So let's say we have this sorted vector. All we can do is we can iterate on the element which is going to be the first element. We can iterate on the teleporter which is going to be the first one. So let's say this is the first elevator. So this is forced to be of type 1. And now what we can do is, since we have all of them to be sorted, we can just do a binary search to figure out uh, how many teleporters we can use, which will cost us less than C. Now, there are two cases. So the binary search ends somewhere here, then it's good enough. But if the binary search ends here, then that means it is taking this element into account. So then we'll have to somehow not take it into account. Okay, so in that case, what we'll do is we'll just increase the binary search query by uh, this much amount, right? So that's, yeah, I think that's self-explanatory. So that's a much better way to go about it, right? So in that case, we won't even have to store the types. Yeah, makes sense. So instead of a normal vector, let's take a vector of pair. And let's take a vector cost. And we'll read in all the costs. Now AI dot second is definitely going to be I, but AI dot first is going to be the minimum of two values. First is going to be I plus cost of I, and second is going to be n plus 1 minus I plus cost of I, right? N plus 1 minus I plus cost of I. Now, as always, I am going to sort this vector. And then I will have to make the prefix sums of this vector, obviously. So prefix sum of I is going to be prefix sum of I minus 1 plus AI dot first. Cool. So now we'll iterate on the element which will be our first teleporter, right? So it will cost what? So the IDX, the index of that elevator is going to be AI dot second, and it will definitely be costing us cost of IDX plus IDX. So if this is the original cost and this itself is exceeding C, then it doesn't matter because it can't be the first teleporter that we use, right? So we'll simply continue. Now, this much has already been costed to us, right? So the remaining cost that we have is C minus cost of IDX minus IDX, okay? Now what we can do is we need the first J, or maybe we need the last J, such that P sum of J is less than or equal to this remaining cost, right? So let's say J is the upper bound of all the prefix sum values and remaining minus prefix sum dot begin, J minus minus. So this value of J is going to be the last J such that the prefix sum is less than equal to rem. Now there are two cases if J is smaller than I or otherwise. So if J is smaller than I, then we can be sure that we can take all the elements from 1 to J. So we can just say answer is max of answer and J plus 1. Since we are taking I as the first element and all the elements from 1 to J. Okay, but that's not the case. Then what we'll do is we'll say rem plus equal to the cost that we just had. Or maybe obviously rem plus equal to cost of IDX plus IDX will just be the equivalent of saying that rem is equal to C. So instead of having the upper bound of rem, we'll just have the upper bound of C, and we'll take all the elements from 1 to J. Here we can assert that this J is greater than or equal to I, and this will always be true. So answer will be max of answer and J. Right, so hopefully this is correct. Yep, this works. Now again, we'll have to wait to see if we pass. So we passed F, that I already knew. Did we pass G1? Yeah, we passed G1. Now all we have to do is wait for us to see the verdict of G2. Till the time it's happening, let's just cross-check our code. And let's see if the samples were even strong or not. There are a lot of samples, so probably they shouldn't be that weak. So this is what we will have, minimum of this and this. Then we'll sort all of them. We build our prefix sums. That's correct. Then we have this index. So cost of index plus index is what we'll have to take. If that is greater than C, we can just continue. Then this is going to be the remaining value. So we take its upper bound in the prefix sum, decrement it by 1. So if this is less than I, then we can just take it. Otherwise, that means that the prefix that we have will just have the index I. So we can just take the upper bound of C and we can take the first j element. So that seems correct to me. Should pass. It's running on test 2 and it does not pass. Now that is weird. So is there something related to n being equal to 1? No, that shouldn't be the case. So did I make the observation wrong that for all the subsequent elements we have a choice? I don't think so. So why did we get a wrong answer here? I plus cost of I, n plus 1 minus I plus cost of I sounds reasonable. Then we sort all of them. Then we build the prefix sums. This index is going to be ai dot second. You have C coins, you start at 0.0. What's the most number of teleporters you can use? Oh, I think I know where I'm going wrong. Yeah. So the problem here is that I am assuming that I am taking this first element as a type 1 element. So I'm forcing that to happen, right? So I just can't take C here. What I will take instead is, since I took cost of IDX plus IDX, I'll have to update the prefix sums somehow. Okay, so rem will be C, but instead what we'll do is, let's say we have a previous value of prefix sum is equal to p sum of I. Now we'll say p sum of I is nothing but p sum of I. Oh, we need to update all these prefix sums, right? Okay, yeah, that's going to be a problem. Yeah, now I know where I'm going wrong. It might be the case that the ideal value of prefix sum of I, the ideal value of A of I is of type 2 and not of type 1. Okay, yeah, that's going to be problematic. Now, how do we handle that? Hmm. Yeah, so here's the thing, right? Uh, I'm sure that I'll take all these values. So this is p sum of I minus 1 plus cost of idx plus idx. This is something that I'm definitely going to take. And now I need to take some extras. So I will subtract from C this value. And I want p sum of j minus p sum of I to be strictly greater than, let's say this value is rem now, to be rem. Yeah, so this way I can handle that. So rem is equals to C minus p sum of I minus 1 plus cost of idx plus idx, right? Yeah. So now we want p sum of j to be greater than rem plus p sum of I, right? So we'll take rem plus p sum of I. Hmm. So we can say j is equals to upper bound p sum dot begin plus j plus I plus 1 p sum dot end, and this is going to be rem plus p sum of I minus p sum dot begin and j minus minus. So now the number of elements that I'm taking is j minus I plus 1. Yeah, this works and this should pass. Hmm. Should I have a plus 1 here, or should I have just plus I here? Not sure. Yeah, let's have a plus 1 here. And then how many elements am I taking? So first of all, I take the first I elements without question. And then I take the elements from I plus 1 to j. So that's going to be j minus I elements, right? Yeah, so this is just going to be j. So we take the first I elements and then we take the elements from I plus 1 to j. Which is j minus I. But what if j is equal to I? In that case, we take 0 elements. Yeah, this should pass. So let's submit this now. Meanwhile, let's also verify. So I am taking the first I elements, and the value that I have is this plus cost of index plus index. So the remaining is going to be this much. And I think I still missed one case here. Yeah, so if this remaining is less than 0, then I can say answer is equal to max answer and I minus 1 and just continue, because I can't even take the first I elements. Yeah, that makes sense. But now I know that I can definitely take the first I elements. So then I take the first I elements and I figure out how many extra elements I can take, which is going to be this value minus psum dot begin minus minus. Yeah. Hmm. So let's submit this as well. Oh, I already got accepted. Yeah, so I think that previous solution was somehow taking care of this case itself. So yeah, we are done with the contest. Let's see how we did. Pretty bad as expected. We took around 160, so we took a lot of time. The rank itself is not that good. But in any case, I think that's it for today. Hopefully you guys enjoyed the stream. That's going to be it.